Good morning, welcome all. And so we are very glad to see many new faces and many old faces as well. We will start the lectures in another 15 minutes. But before that, I would like to invite Professor Smenta Wadia, the founding director of ICTS and currently the Infosys Chair Professor, to say a few words about the ICTS, the idea of ICTS and the mandate of ICTS.
Thank you, Ajith, and good morning, everybody, and welcome to ICTS Bangalore and good weather. I'll just give you a brief overview of what we are, and I'm sure in the 2 weeks that you are here, you will find out a lot more about us and also our campus, our facilities, and our people. So, from the beginning, the idea of the ICTS, or its goal, ultimate goal, is to bring together physicists, astronomers, cosmologists, mathematicians, all biologists, all the peoples actually involved in the basic sciences to come together under one roof, and from all over the world, not only from India, but after all, as Feynman said, it's a small rock, and peoples from all over this small rock, we would love them to come here. And for what? To work together to solve some of the most challenging questions posed by nature. And that, of course, includes my mathematics friends also. I mean, I think they also solve problems posed by nature or their brain, which is part of nature. And the other thing is to provide advanced science education, as you are all here for. And the last point the ICTS would like to sort of, carry forward is to help create scientific temper in society, to really infuse into our population, the idea of what is truth, ultimately. Okay, so with this few words about what we would like to do, what we are and what we are doing, I'd like to tell you that this is basically enabled by 3 interactive missions. And the first 2 are the really basic ones, programs, which I will explain what it is. And then in-house research. And based on the resources of 1 and 2, we also have a very strong science outreach because of the resources available from the programs and the in-house research. So these are our facilities. Just for those who just walked in over here, you will have a look at our campus, our library, our other facilities, and the hidden works of art, as you see in the bottom of the picture. So what are ICTS programs? We've been having programs since September 2007. And programs include pedagogical schools, workshops and conferences, and discussion meetings. Since 2007, ICTS has organized around 138 programs with 61 discussion meetings, and over 6,000 participants have participated in these activities. And it has had a tangible impact on Indian science, without doubt, actually. This is a list of programs which illustrates to you that ICTS is interested in the full landscape of the basic sciences. And you can see some of our thoughts over here. So programs are a new model for scientific exchange and collaboration in India. This is a unique institution in India today. And it's a place to gather researchers to brainstorm, to incubate new ideas, to chart out roadmaps. And of course, it also has a strong pedagogical component that benefits students, postdocs, and senior researchers. In fact, I feel that I miss a lot not attending ICTS programs, but you can't attend everything because you're a student all your life, actually. There's always so much to learn. And our talks are archived on the YouTube channel called ICTS Talks. And there are some tens of thousands of subscribers already. So here are a few sample programs. So as you see, the full landscape of the basic sciences is there, from mathematical things to condensed matter, to biology, to astronomy, astrophysics, statistical mechanics, yeah, all of it. And we actively try to cultivate this idea at the ICTS that science has no boundaries, basically. These boundaries have been created by our inability, perhaps, of the type of species we are to comprehend so much all at once. So now we try to piece it all together. So the other thing we have, other discussion meetings or named lectures, which have been very successful, are in honor of Subramaniam Chandrasekhar. So we have the physical sciences named lectures. Around each named lecture is a discussion meeting. This is a thing that has worked very well at the ICTS, especially in physics, because ICTS was started by physicists, so clearly, I mean, you see a lot of physicists here to begin with. We have the mathematical sciences named lectures after Srinivasa Ramanujan, and the lectures in biology, computer science, engineering, and related areas in honor of Alan Turing. And you can see all this galaxy of people who have given these lectures and participated in the corresponding discussion meetings. Okay, so the next thing is that besides the programs, ICTS, when we conceived it, we also thought it should be a platform for new initiatives, you know. I mean, I found that in India, actually, it is very difficult to do something new, you know. I mean, it's not easy. So we created ICTS also in part to be able to be a platform for new initiatives, like the monsoon initiative that is going on at the ICTS, which involves mathematical foundations of the monsoon system. This is not being done anywhere in India today, actually, you know, mathematical foundations. So we have initiated that. Then we are a nodal center for LIGO India. In fact, ICTS, I think, played an important role in the LIGO activity since we had Ajith and Bala over here. We also have the Cowley Asian Winter School on Particles, Strings, and Cosmology, which rotates between Korea, Japan, China, and India. So every 4 years, there's a cycle that comes here, and it's a very major school in Asia. So in this way, we are trying to, do something which the Lejeune School in Europe has done, actually. It has really created a large scientific community after Second World War. But some of us felt that we should do similar things in India, actually, and in the Asian region, South Asian region. So we joined hands with Koreans, Chinese, and Japanese to do this. We also have this ICTS Brandeis NSF schools on statistical physics every few years. Mathematics of Planet Earth was a program at the ICTS in 2013 to, I'll say a little bit more about it later. And we also did the pilot phase of India Light, which is the large data high-speed network. And we also run summer courses by very distinguished scientists. So till now, the initiative of Ajith and Bala has been to invite Professor G. Srinivasan to give these courses. But in the future, we'll have other subjects also covered by eminent educationists and researchers, actually, every summer. I think this is a very important activity that Ajith has started over here. Okay, now I come to the second, the real foundation of the ICTS is this. And it is its faculty and its research. So we have, I'm going to sacrifice modesty for truth to say that we have the highest quality faculty in theoretical sciences in several areas, in the best in India, actually, already. And it has strong core strengths, but all these people have interests across disciplines, you know. They talk to each other or at least have a conversation. And presently we have 17 regular faculty, and one is about to join in September, a mathematician. There's a junior faculty, there are 2 Infosys chairs, like Bala Iyer is one of the Infosys chairs. And there are 2 visiting joint professors also. Okay. Okay, so this is a photograph of some of our faculty. You'll see them around over here. And okay, so what are the research areas? So here is a list of the research areas in which our faculty is involved in. Dynamical systems, data assimilation, uncertainty quantification, that type of mathematics. And this is all relevant for the modeling of the Indian monsoon and other areas of earth sciences. Statistical physics, condensed matter, fluids, physical biology is one set of subjects which basically deal with complexity, complex systems. And we also have interdisciplinary mathematics. Especially now we have hired 2 outstanding mathematicians doing probability theory. Gravitational-wave astronomy, of course, ICTS is well known for its contributions. And we also have string theory and quantum gravity, people who want to discuss questions which are fundamental, actually, connected to the origin and the future of our universe. Where did we come from and where are we going? Today there's a lot of controversy about where we are going, but anyway. So we have a very strong postdoctoral and graduate program in physics and mathematics, okay? This is also very important. It's part of the in-house research and academics. So we have a huge number of students now, This year, 15 students joined. So the ICTS has to expand, it has to become big. So we'll try to do something about that also. Anyway, so this is the younger people who are on campus, and yeah. All right, so as I said in the beginning, we use our resources for programs and in-house research faculty to do science outreach. Now, science outreach is very important, especially, I shouldn't say especially in India, it's also important in the United States. I mean, as you know. It is basically to simulate and harness young minds of India, inculcate scientific temper in civic society, and inform civic society about contributions from India to science, engineering, and mathematics. We are looking for support of our society, of our people, to support basic sciences, actually. And this is one of the reasons why this activity is very important. It's not only for support, but there is something intrinsic about doing this, to change the culture of our people, actually, to be more scientific in their outlook, in every aspect. So we have public lectures, Einstein lectures, and we have this Kaapi with Kuriosity, which I will mention a little bit, and the Vishveshwara Lectures, in honor of Professor Vishveshwara, whom you must be all knowing about. So these are the public lectures, just an illustration of some of the very eminent people who have given public lecture. And you just see the number of people who come for it, actually. It's quite amazing. We also introduced the new lectures this year in honor of Professor D.D. Kosambi. I don't know whether all of you know about D.D. Kosambi. He was the first mathematician to be hired at the Tata Institute of Fundamental Research, but his great contribution is the scientific approach to Indian historiography. And we thought that we should also have lectures in this type of areas at the ICTS. Okay. So this is the Kaapi with Kuriosity. It's a monthly event at the planetarium, fantastic success, where we invite leading scientists and mathematicians, actually, to come and speak to the public and civic society and to students, etc. And so this has been a great success. This is the Vishveshwara Lecture. This is the inaugural one, and it was like a rock concert by Professor Kip Thorne. So a lot of activity about this type of things actually going on over here. This is the exhibition we held in 2013, and we also celebrated 10 years of ICTS with a major event this January, in which lots and lots of very interesting things happened. And one of the things we did was we organized a panel discussion on the usefulness of useless knowledge. You can look it up on the website, what all this is. And finally, I would like to end this because I think I've overshot a little bit. I would like to thank Ajith, Arun, and Bala for organizing this school. And I think more so for these incredible efforts to create a community of young Indian scientists in this area. I think this is very, very important, and I wish you all the best, very best. Thank you.
Thank you very much, Svante, for the very kind words and these warm words of welcome. So we are starting the academic program very soon. The first course is by Andrea Maselli from Lisbon on exotic compact objects and their gravitational wave signatures. It's a very active area of research now. This is sort of, I would say, it's a rather new topic also. So we are trying to, and there's a explosion of knowledge especially after the discovery of gravitational waves in the last few years, and we thought it's an appropriate time that we learn about this from one of the top experts and the top groups in the world. So with this, few words, I would like to now invite Dr. Andrea Maselli from Lisbon to give the first lecture. Thank you very much.
Okay. First, let me thank the organizer for inviting me and talk about, well, a general subject, which is strong gravity. So let me say from the beginning that I think I'm going to disappoint you several times, because we're going to talk about exotic compact objects, but probably just at the beginning and at the end of these lectures. And for the simple fact that, well, I wanted to introduce some basic concepts about perturbation theory that, is going to be used for exotic compact objects. But I think that the best way to introduce this is to use like the general relativistic example, so to start from perturbation in general relativity, and most of all because then the majority of the compact objects that, well, are nowadays available in the market and we study are actually, again, solution also of Einstein equations. So essentially what we are going to do, well, in the next 5 days can be applied very, very easily to exotic compact objects like, well, you will hear about boson star, gravastar, wormholes, and so on and so forth. So the basic idea in these 5 days is to develop some techniques about, well, normal modes, tidal law numbers, some names that I hope they will become a bit familiar later on, that then you can shift from regular black holes in general relativity to other objects, okay? So let me give you just a brief introduction about what we're gonna talk. So this is just a general slide about the where you can find some useful introduction, some useful references on the topics. On the left there are, some books, and I will mostly follow the path by these two books here. Okay, there is the very extensive book by Chandrasekhar, and then there is also the 2 volumes of Michele Maggiore about, the first one is a bit more technical, the second one, Gravitational-Wave, is a bit more applied astrophysics. And then there is, I will also follow this series of lectures of Emanuele, and that also because we are working together with Emanuele, Vitor, and other people to finally change this thing into an actual reviewer book. I haven't understood completely which is the end point of this. On the right-hand side, actually, there are real paper literature, okay? So to me, the first 2 are like probably the most important, because the second, third, and fourth lecture will talk about quasi-normal modes, and these are, really 2 beautiful papers. These are the seminal works about stability of black holes. And so the Reggie Wheeler, I just copied to the same. So this one is, of course, Reggie Wheeler. This one is by Frank Zerilli. So it's not Reggie Wheeler, but it's Zerilli. And then there are these other four papers that are related to exotic compact object, okay? So there is these first two works by Kostas Kokodas and Valeria Ferrari and Kostas Kokodas that actually are devoted to study perturbation theory on, something which are like extremely compact stars, okay? Stars with constant density, so that violates some basic principle of nature like causality and so on and so forth. But these are like prototypes of exotic compact objects that then became pretty famous also later on with the studies by Cardoso, Vitor, my boss, then Paolo Pani. And this is a review about most of the phenomenology that we can have in gravitational waves and through electromagnetic signals from exotic compact objects as we intend in the modern literature. In the last day, actually, I will spend all day talking about this paper by Mark and Zimmerman. And this is a very, very beautiful paper because it gives you a kind of recipe to study ecos, okay? So, a class of exotic compact objects, as we will see maybe a bit today and then at the end of this lecture, can actually feature some extremely new characteristics, which are ecos, so repeated pulses in the perturbation spectrum that you get from this object. And I think that studying this paper is very, very useful in order to understand the basic physics behind these ecos that we will see, that we can try to see if exotic compact objects exist in nature. So, just a bit of introduction. I mean, I think that there are some people that I will also quote here that, black hole history and the history of, and then, coming from black holes to exotic compact object is quite large. And, really involved most of them, most of the brilliant people in the world. So there is this basic idea that everything started with this philosopher Mitchell, that just, probably one day thought what would happen if you have a star so dense that not even light can escape. And the starting point of the black hole history, is devoted to, I'd say, the poor Kash Varshid, because he didn't have too much time to think about black hole because you have to run to the war. Indeed, there is this famous citation, this is like an exchange of letters between Schwarzschild and Einstein, and as you can see, he was really fighting the Russians, and in the First War, there is this letter in which, even at the front, he was actually writing, doing current research, and actually probably some months later, Einstein was presenting in Europe somewhere some of the results that Schwarzschild had found about the non-rotating stationary solution in general relativity, okay? And then there is this another famous quote by Chandrasekhar. I think that really explains the beauty of black holes that are the elementary particles of general relativity. So you have something which is probably one of the most fundamental objects in nature, because as far as we know, it's just made of pure gravity. Okay, it's an elementary particle. Okay. And it's extremely, extremely nice that in order to describe all the families of black holes that are in the universe, you don't need like, something like standard models or not a big, but a table with a lot of rules. You only need 2/3 quantities, so mostly mass, angular momentum, and charge of the black hole. So with these two quantities, you can take all the black holes that are in the universe and you can describe them. Okay? No matter, this is like the Noether theorem. Okay? No matter if you put all the woods that you have on the Earth and you compress to prepare a black hole, or you have a dark matter star, at the end point of the evolution, the only things that will distinguish these two guys will be the angular momentum and the mass. Okay? And this is a remarkable thing. And then, we went a lot of mathematicians up to the, Kip Thorne is just the end point of, at least so far, of all this story. I want to also give you just an overview of where we are looking for and which are the experiments that we're going to use to characterize black hole. And this is a plot by Tessa Bakker and other. So this is a plot in which we have two quantities that can characterize the strong field regime of the theory that we are going to study. Actually, there are several parameters, and just for sake of simplicity, these are two that can be easily understood. The first one is what we call the compactness. Actually, in geometrical units, this is just what probably for neutron star you already seen. Something white. No, okay, I will use so the first parameter is just the compactness, okay? In most of the lecture, in all of the lecture, I will just get rid of C and the gravitational constant, and I will use geometric units, okay? So this is a kind of a very nice parameter to characterize what can also be called like the surface gravity, okay? And the basic idea is that, for example, for the neutron star, we have this parameter, the compactness C, which can go between these two numbers, 0.1, 0.2, and mostly the edge of these two numbers is mostly set up by the kind of matter that you put inside the neutron star, what we call the equation of state. For Schwarzschild black hole, we have that this thing is exactly equal to 0.5, okay? The goal of people that study exotic compact objects, and I will show you later, is find something between these two objects, which is actually more close to the black hole limit, okay? That it actually can be so close that we hope that is distinguishable, but, well, closer it is, more interesting will be at least for the level of fundamental physics, okay? So, here I just draw an imaginary line where there are like the black holes, all the non-rotating black holes, okay? So the Schwarzschild solution here. And depending on the mass of the typical object, you will have different curvature. This is just, if you think, it's just, well, the tidal term, okay? This is like the leading term. If you take a post-Newtonian expansion of the, like the Riemann tensor, this will be the leading term that you will get for the curvature, okay? It goes like the inverse of the mass square. And so depending on the mass of the object, you could have stellar, intermediate, and supermassive black holes, okay? And these three patches also do not cover only, I mean, three different, well, different zones in the curvature here, but also are covered by different experiments, okay? So fortunately, we have a lot of stuff experimental-wise going on there. So we have really 3 running interferometers. Virgo played an important role for the neutron stars. So Kagra is also joining very, very soon. There is LIGO in India. And with this, I mean, we will have a network of 5 detectors, stellar detectors, as a ground-based detector that will cover something up to 10 to a bit less than 10 to 4 solar masses for black hole, at least to detect the binary spiral of this. Then when you want to go to higher, larger mass, you have to go to the space, okay? Because if you increase the mass, you are just shifting the gravitational wave frequency of your emission to lower value. And this is, I think, I don't know anymore how it's called, because I mean the American joined again the quest for LISA, but we will have, well, pretty soon in terms of space mission, because it's going to be in 2030 or 34, LISA. There is also the SIGO, these satellites that will cover an intermediate band between LISA and LIGO, Virgo detectors that also is going soon. And also, well, in Europe there is, and also in US, there is a large attention for this called third generation detectors, so ground-based detector that should go at least 1 order of magnitude in terms of sensitivity better than current detectors here, and that will be in this zone here, but will really, really boost the sensitivity of the detectors above the edge of the spectrum, so at the low frequency regime and possibly even in the high frequency regime. But the important thing is that is a bit light, let me remove this color here, is that there are also other facilities that we will use in the future, okay? And actually some of these are also currently used, like for example, these Event Horizons, the telescope, or the black hole cam. So there is a synergy, and actually gravitational waves can join the quest for what is called the multi-messenger astronomy, astrophysics. So there is a particular class of satellites that will help to understand some basic feature of this exotic compact object through a plethora of phenomena that can be from the black hole shadow to other phenomena which are called quasi-periodic oscillations around compact object and so on and so forth. This is just a prototype loft, actually, a satellite that was a very nice mission. Well, it did not survive to the running of the ESA mission, but it will probably be launched in a different configuration by the Chinese astronomical community. So this is more or less the standpoint, how we call where we are today. Okay, so in purple there are these well, let me call candidates in the X-ray, so in the electromagnetic bandwidth for black holes, and these are the events that have been detected with LIGO. Okay, so there's with this zoo of objects, and I mean the detection were pretty. Well, they were really astonishing, and they just, well, okay, most of the people believe that it was true, but they say that we had a striking confirmation that we have black holes, that black holes may form as binary, and that black holes in binary may merge in a reasonable amount of time, okay, Hubble time, okay. This was kind of, well, immediate consequence of the detection. There were a lot of tests of general relativity and on the parameters coming from the black hole events, but I think that, well, one of the most intriguing one was something that the collaboration has done, I think only in the first paper, because it was the one which allowed to explore a bit the last part of the signal, that it was the first attempt to detect the quasi-normal modes, okay? And we will see later on what quasi-normal modes means in terms of terms. And so the oscillation in the post-merger phase of the black hole, and this black ring here should identify the most plausible interval for the parameter of the decay time and the fundamental frequency of this oscillation of the post-merger phase of the object that are formed. This is a really, really first attempt because the signal-to-noise ratio, so the strength of the signal was not as strong as to make really a huge claim, but this is a first attempt, okay? We have, well, people way before me have dreamed, I mean, for decades about this kind of possibility, okay? So this was the first, and probably in the future, with all the detectors that we'll have, we will be able to use this to really see oscillating black holes, so this fundamental particle ringing into the universe. So the natural question about this is, after this, okay, everything is clear? Do we understand everything about black holes? Is there any other open possibility to explain extremely compact object that can mimic the coalescence that we have seen through LIGO and Virgo? So I put here these question marks, and so why are we looking for the alternatives? Well, there are several reasons. I mean, mostly of these are really physical reasons, like there is this long, well, infinite problem about quantum effects, and mostly related like to the quantum nature of black holes. There is like the problem that black holes outside are pathologically free because we are very well protected by the horizon, but inside, who cares? Who knows what's going on? There are problems like Cauchy horizon, and I think that these are all very, very good statements, but for me, well, the point is that probably, at least for now, one of the most striking points is this one, and this is in general the way we should do science, that whatever you have something, don't believe that this is, well, at least in my opinion, we will never have the description, what nature has put inside the universe. We have a description of something, and we have to keep challenging this description. The point is that if you don't devise alternative, you cannot challenge the description that you believe is the most accurate so far. Okay, so if you want to test something, you have to devise something to test against. Okay, and this is one of the main reason why we should keep working on exotic compact object and devise strategies, phenomenology, what else. Okay, and most because finally we live in a period in which we are dominated by data. Okay, I'm a bit young, so probably I didn't live too long for this, but most of the people before my generation work in a period that were completely dominated by theoreticians. Okay, there was a theoretical side that was completely over on top of this. Now, I mean, we have data, we have a lot of data, we can test the ability of this data and actually the edge of current instruments to go up to a certain point in testing strong gravity, okay? So I think that this is the main question that we can try to solve with gravitational waves and, well, even electromagnetic signal, but in this lecture with electromagnetic gravitational waves. And so if black holes are really the end point of stellar evolution, maybe there is some process, physical process, that we don't understand or we don't know at this point, that can stop the formation of the singularity, okay, and the formation of the horizon. And if whatever we find an object which can be as compact as a black hole and does not have any horizon, okay, this particular feature, we call it exotic compact object, okay? The question is, if we have something extremely compact at the limit of a black hole, can we find some features that will help us to distinguish between this particular guy and a regular black hole? Well, the answer is that there are gravitational wave signatures we will use in all the parts of the spiral of a binary waveform. Okay. Let me say that there are a lot of problems before actually just investigating exotic compact object. Okay, so you can do all the math that you want on an exotic compact object, but there is a large uncertainty on the formation of these objects. Okay, so it's not clear how these things can form in nature, apart from boson stars, in which there are like some mechanisms that well, can explain you like the aggregation of like complex scalar field and the formation of massive objects. For the other like possibilities that we have in nature, the situation is really, really far from being clear. We don't know absolutely from this which are the possible channels that can produce that can lead to an exotic compact object coalescence. So you can have one of these possible mixed channels, and we don't know so far. So there is a lot of work to do about evolution, detection rates, maximum masses. There's huge work to do, okay? And also work in realistic astrophysical environments. We know there are black holes with accretion disk. Can we devise this kind of stuff also for exotic compact objects, and maybe study the accretion processes and the phenomenology in the electromagnetic band if there is from these processes? So there is a lot of work to be done in this field, okay? But let's assume that the exotic compact object exists in nature. What we want to, and in this slide I want to give you a very rough, but just intuitive characterization of how we can classify exotic compact object, okay? The easiest way to classify exotic compact object is to use the compactness, okay? And in particular, what we can use is the radius of the compact object here, okay? On the x-axis here, there is, well, some numbers that, well, actually we will review today, but I think that most of you already know. So we have the innermost stable circular orbit, the last stable orbit for circular particles in geodesic motion around the compact objects, around the, well, yeah. Then we have the photosphere, the analogous for this, but for massless particles. Then we have the Buchtal limit, okay, and which is the maximum radius, well, minimum radius that a neutron star, a regular star, can have, just requiring some very, very reasonable assumption about physical requirements inside the star, like monotonically decreasing energy density, causality, and so on and so forth. And here, the black hole limit, okay, for Schwarzschild solution, okay? When R equal to M, we have the standard black holes, okay? So here, this is the domain of the neutron stars, okay? Depending on the, well, this is very, very high as a limit, but depending on the equation of states, on the nuclear matter that you put inside the neutron star, we will have something inside this rectangle. This is the domain of exotic compact object, okay? So something which can be as close as to a regular black holes. And in particular, what we can do is actually parameterize the radius of the echo through this quantity here, okay? So we can parameterize the radius of the echo as 2m times 1 plus epsilon, which epsilon is a can be a very small parameter, okay, which can be, well, as small as 10 to minus 30 at the order of Planck length, okay. So actually this is, well, a coordinate, not a coordinate invariant measure. You can also devise, if you compute the proper length of this object, it will be something like this, okay, if you want to compute the proper radius of the echo. But this we scale as a power of epsilon, okay? But for most of the feature that we see of like a deviation of the quasi-normal mode spectrum from the black hole one, or the tidal love numbers of an echo with respect to the one neutron star, most of the feature will go as log epsilon, okay? And since this is a very small numbers, using this formula or the proper one makes absolutely no difference, okay? So we will use this thing here, especially in the last lesson, to characterize like the radius of an echo. Okay? We have something that, an object, that it would be with a radius that is just shift from the, well, Schwarzschild radius of a very tiny parameter. The crucial point is that the echo does not have any horizon, okay? This is a real surface at this epsilon, okay? And this surface will change everything, okay? Because, well, especially when you compute quasi-normal mode, essentially, well, the only interference that, well, the only things why black hole matters, and we'll see, the horizon matters in quasi-normal modes, is because it set up some particular boundary conditions, okay? Ingoing boundary condition, because, I mean, black holes are just like beans, so whatever you put inside, they will never go out. In this case, if you remove the horizon, you're just removing an important decay channel, okay, something you don't have this one-way going membrane, and so it will change completely the boundary condition. The goal of like astrophysics will be, okay, let's assume that instead of a black hole, we have an echo which is really close to a black hole, okay? There are models of echo can be as close as this, even with more nines, okay? So you say, and these nines actually reflect in really microphysical processes that can hit this surface at 1 plus epsilon, okay? Well, our neutron star with like constant density can be like, we can have, I think, yeah, even a radius like compared to the photosphere. And for me, this is an exotic compact object, okay? Something that, well, has a radius 2m, 1 plus epsilon. This epsilon can be large or small, depending, of course, the most interesting one, if you take like a wormhole or, well, no, a wormhole has like something at a throat. But you can take a boson stars, and in particular cases, it can be very small, or you can take a gravastar. Okay, this belongs to evolutionary scenario, like, well, I don't know how to produce a gravastar, this kind of object with negative pressure and like some kind of form of matter, thin shell of matter. So I will assume that there is well, we will assume that, I mean, these objects are there and they have this characteristic, okay? The point is that, well, you see, this is, so there is one side of the physics about this, is that producing the model. And there is the other side, which is detecting events and devise strategy and identify parameters that don't necessarily need, well, the structure behind. So I can, there are, well, for exotic compact object, there is a huge part of the community working on agnostic tests, okay? I find a parameter into gravitational wave. This parameter should be a precise number for black holes, like log numbers. So it should be 0 for black holes. For a neutron star is a particular value, for exotic compact object is another value, okay? I don't need to know that the formation scenario for the exotic compact object, but if I take the log number, and I'm 100% sure, some that will never happen, but let's just assume for simplicity, that is different from 0, I can rule out a black hole. If the object is extremely also compact and cannot be a neutron star, so there should be something different, and then let me call it exotic compact object, okay? So, yeah, there is a zoo of objects that I don't know, and that I'm really not interested into it, okay? From my side, you can devise any model you want, okay? I don't want to fight with the high-energy people, or there is a large community devoted to talk about football, anisotropic stars, quantum star, fluids. I mean, boson star, there is a huge zoo of this. I mean, Everyone has in some reason and psychological way to think about this. I'm not really interested in to go into the challenge of the objects. Okay? What I'm going to do to study is how, if these objects are there, how they will impact on the gravitational wave phenomenology. Okay? And which are the parameters that will best characterize these things. This is my main... but by the way, this is really... Now, this is a bit more extreme because, okay, you need more physical explanation for this, okay? But this is not as different as from the problem of neutron stars, okay? Because for neutron stars, you have a zoo of equational state. You have a lot of equational state, which means a lot of way to describe matter inside the neutron star, okay? You can measure the parameters, and then the difficult part will be trace back the parameter to the real equational state. Now, of course, for the equational state, we are guided also from terrestrial experiments at low density because we have all the stuff that comes from LHC, like heavy ion collision, whatever. In this case, it's a bit more speculative. But the process is the same, okay? Even for neutron star, in principle, I have the gravitational wave which depend on some parameters, in this case, the love number, and I can measure this, and then I can all work way back to identify the equational state that has produced this particular parameter. Of course, in this case, it's more speculative, and I don't want to go into the battle, okay? This is an important problem, it's a very good question. So, well, most of the problem comes from like rotating object. So essentially all the, so there is all the objects which have a photosphere and which are rotating have this kind of super radiance instability, okay, ergo region instability, which is connected to super radiance, so extraction of energy from this object, and the problem is that there is no horizon there. And well, when you talk about instability, there is one problem, which is that unfortunately, well, fortunately, we still work on this object because we don't know the dissipation effects inside this object. Okay, this could be, as for neutron star, it could be another channel that quench the instability. And the other is that whenever you find an instability, and this is like a general argument, you also need to set up the time scale of this stability. I mean, if it's longer than the age of the universe, who cares? Okay, and but there are a lot of studies, I mean, going on for this. So the situation. You have to model ecos. No, you have some realistic models. I mean, I can give like the action of a boson stars, and from there you can derive like the equation, the Fields equation, and compute the structure as you were integrating the TOV equation for a neutron star. Yeah. Oh, it's good that, well, okay, we won't do probably anything today, but, okay, this is like where we're looking for. Well, don't be too much excited because after this slide we won't talk about any other exotic compact object until the last lecture. So I just want to tell you where we're looking for echoes. Okay, this is like the most used plot probably that people in gravitational waves have seen. I just want to tell you where we are looking, which are the signatures that we want to find in order to distinguish regular black holes from echoes. Okay. And well, at least these two will be based on the mathematics that we're going to develop in the next 4 days. Okay, so you have the coalescence of two objects. Okay, it reminds that well, I want to look at these things. I'm looking from one side. I have two black holes. From the other side, you have two exotic compact objects that for me are two extremely compact stars. Okay. When I say stars, I mean that there is something which is not vacuum, there's not horizon, there is something inside. It can be any form of incredible imaginative matter, but there is something inside that let me call, yeah, for me, like another synonym of exotic compact object is compact star, okay? When you are far from the coalescence, okay, you don't see, I mean, whatever you put, two black holes, okay, two delta Dirac or two stars, you will never see, it will gonna be extremely difficult to distinguish them, okay? These objects really behave as point particles, okay? As soon as the coalescence goes, I mean, into the high dynamical regime, there is something that we well know well, for like tides in Earth, which are tidal effects, okay? So these objects, the exotic compact objects, are tidally deformed, okay? This is something that we know how to do extremely well with neutron star because LIGO has already done this kind of analysis, okay? So essentially the two stars, the two exotic objects are deformated by the tidal field produced by the two-body system, okay? And the size, the magnitude of the deformation depends on the particular matter that is inside the exotic compact object, okay? Now the point is that, I will probably show, yeah, this is something that you will develop in an exercise. So, in general relativity, well, actually even Newtonian physics, in general relativity, we at the linear order, we quantify the effects of tides through this equation here, okay? And this quantity here, this one is the so we have from one side the quadruple tensor of the deformed object, from the other side the tidal tensor, okay, which is a pure geometrical object, and this guy here, should have used another color, is the love number. Okay, this is a very, very nice equation because on this side we have well, the effect of the deformation, so in which way and how much the object has been tidally deformed. On this side, we have the source of deformation, and in the middle, we have the coupling parameter of this deformation, which is this object, which is a constant parameter, and is called the love number, okay? This is, to answer one of your questions, this is one of the agnostic parameters that you can use to distinguish echoes from black holes. Because this object, lambda, is equal to 0 exactly for black hole, and is different from 0 for echoes, and is different from 0 for neutron stars. Okay? So this is really a null test. If you are super confident that this object is different from 0, you can already exclude this from being a black hole. And this is a completely agnostic test. You don't need to know anything about the structure of the echoes behind this thing, at least to detect them. Okay. So this is tidal effects. Then there are spin deformation, and this is more or less the same game here. So you have deformation induced by the rotation of the object, and well, this is for black hole, the quadruple induced by rotation is very, very well known, and it just depends on the mass and the spin. While, I mean, it's different from exotic compact object because it will depend on the, well, integrating in the destruction again inside the object, so you have to integrate the source equation. This is another tool that you can use to make agnostic constraint. I will drop the absence of the horizon, and then, and this is the subject of these lectures, at least the quasi-normal modes, and in the last lecture will be the echoes, we have the quasi-normal mode spectrum, okay? So, at the end of the coalescence, you have like a black hole which is outside equilibrium, okay? Is relaxing, emitting gravitational waves until it finds like an equilibrium configurations, okay? And as we know in general relativity, well, these relaxation processes can be described in terms of damped sinusoids, which are called quasi-normal modes, okay? For if the product of the coalescence is an exotic compact object, you can have either a modified spectrum of quasi-normal modes, so simply another series of exponential damped sinusoids with different frequency at damping times, which do not correspond to the one that you would expect from a black hole, or a completely different scenario, which comes from the most compact of the exotic objects, okay? And in this case, you will see this kind of guys. Ecos, okay? Pulses. So you have something in the first part which really, really resemble like the quasi-normal mode. And then you have a train, well, multiple trains that will go at the end of the blackboard that actually reflect a unique feature of this exotic compact object, okay? And we will see, I think this is how they are produced, okay? But in order to see how they are produced, we need some extra information. Probably today is going to be a bit of boring because we're going to talk about geodesics, but the problem is that the phenomena that will produce this thing here happens exactly between, well, something that we can identify through, well, we can then associate to the geodesic motion and the surface of the exotic compact object, okay? So today now we'll talk about geodesics. Tomorrow and then the other 3 days, we'll talk about the quasi-normal modes, okay, how they are defined. Actually, since I absolutely don't know, well, if you know or not the quasi-normal modes, tomorrow we'll talk, well, about, I think that the most important thing is that you understand the idea about quasi-normal modes. So tomorrow we'll work about 2 examples which are not really close to quasi-normal mode, but these are classical examples which we can have a really physical intuition about excitation of normal modes. Then we will talk about tensorial harmonic expansion, okay, for black holes, and we'll find how to solve numerically. Then the last day, we will see how to compute this, okay, how to derive the expression not only for the ring down, but also for the pulses, okay. The fact is that whatever the technology will be discussed in the next 3 days, so spherical harmonic decomposition, numerical methods to solve it, I mean, and that we will do in a simple case of GR, they can be applied for exotic compact object, okay? So that's why I want to just study the test case, which is now GR, because we are moving, to devise all the tools that you will need to do actual research, okay? And this also carry to the to the exercise. So we have devised some exercise that are really devised as like homework assignment. So you don't need to finish them. Well, there's no grade, so you can do whatever you want with this. I also prepared, apart from the exercise that will mainly be done, well, you need to do, well, you can do also by hand, but, well, lucky. They will be done with Mathematica, and I also will give you all the Mathematica file with the solution. So for each of the exercise, I have prepared a Mathematica file which solved the exercise. Most of the exercise will be a continuation of the lecture, okay? So it will not be only an application of these things, but since we don't have, well, we only have a finite amount of time, in the exercise will be more argument that you can develop. Okay, so for example, in today, there is work that we talk about geodesics for non-rotating object. In the exercise, you will be asked to devise, well, solution for slowly rotating objects. Okay, and actually, my intention is to provide you Mathematica files and a kind of architecture that you can use to make actual research. I mean, the Mathematica note that I gave you, well, I will give you today is actually being used to produce a regular paper on Physical Review D. So the idea is that you have some tools from which you can really move on without any help to doing real science, okay? And now I think that we can start with geodesics. Okay, we'll talk about particle motions in a generically spherically symmetric background, also because, well, yeah, so far, the only things that distinguish an exotic compact object from a black hole is like the horizon, but you see, most of the phenomena that we'll see at the end from the ring down seem actually to be associated with something that is, well, not very far, but completely different from the horizon, and mostly will be like the ergosphere, okay, the location of unstable orbits for massless particle or waves. So it's very, very important that we study this, and we found out the connection between these unstable orbits and, well, then the emission of quasi-normal modes. I will mostly work just for non-rotating, as I told you, object, okay? I will follow about Bertie and what we have written, yeah, lectures about geodesics. And geodesics are actually, I think that you all know, are actually curves which extremize the action. So in a very, very general framework, even without thinking to general relativity, if you have the action between 2 points with some coordinate variables q and q dot, and you have the action. Okay, the basic idea between the last action principle is that if you have, let's say, the true path, which is Q bar Qi, let's say the true path is the one which extremizes the action, okay? This means that if you have these 2 points and some particular path between 2, and we have a Q trial, this is just a variation, okay, of around the Q bar configuration, with the also assumption that the variation vanishes at the endpoint, okay. The true path, the one which satisfies the equation of motions, is the one which extremizes the action here. Extremum can be a minimum, if this is very short, or can be a saddle point, and this means that ds is equal to 0, okay? And this will give you the Euler-Lagrange equation. Okay. Now, in general relativity, we can start from this action here. Lambda is an affine parameter. I don't need to specify at the beginning which is a proper time or whatever. Okay. And from this, we can have immediately the Euler-Lagrange. Okay, equal to 0. So I think that I won't, well, this is just a very simple calculation that probably I won't think because we don't have too much time, but essentially, if you take this, the Lagrangian here, and you take simple derivative, okay, with respect to x and x dot, you will find the geodesic equation. Okay. Where these are the Christoffel sum. I think that all of you know what is it. I don't need to, let me write just. Okay, this will be the definition of the Christoffel sum. Okay. Oh, from this Lagrangian here, we can study like the motion of a particle with mass or without mass around a spherically symmetric object, okay? And the most important thing will be to study the stability of these trajectories into the space-time, okay? Let me first write the answers for the space-time. Don't need this one anymore. Yeah, maybe if we can, I will be more confident. Okay. So we have only two functions to determine, f and h. Okay, and you know that for star-shaped black hole these are the same, actually the inverse. So this is f is just it was this one, okay. But we will keep at least as far as we can, I mean, completely different because this is more general. And if we have to deal with space-time which are not black holes, I mean, we will have immediately some relation that we can use. Okay. And starting from this and with that set of coordinates, which is of course this one, sorry for that, we can write the Lagrange that will be written before, so like this. In this way, okay? Where the dot here means just derivative with respect to the affine parameter, okay? So for example, this t dot here is the x0 in the lambda, okay? Now, the way it's written is particularly useful here because we can use all the tools that we know from classical Lagrangian mechanics to derive like conjugate momenta and like the equation of motion, okay? So in particular, sorry, you're right. Okay. Thanks. Okay. So in particular, we can define the conjugate momenta, okay? And we can immediately find out from this. So we have Pt, and we just need to derive this with respect to t. Actually, let me define this with a 1/2, so I will get rid of the square. Okay. For this particular system, we also have that h is equal to L, okay? And they are both constant. And we see from here that the Lagrangian does not depend, well, the spacetime does not depend explicitly on phi, neither on t. So it's completely invariant for time reversal, and it's also, you can make any rotation because it's very symmetric. And in general relativity, this means that there are, well, two Killing vectors associated with this. In particular, there are associated with them two conserved quantities that we can call the energy and the angular momentum. And in the standard language of Lagrangian mechanics, these are just cyclic variables, okay? So when your Lagrangian does not depend explicitly on one of these variables, the variable is just called a cyclic variable. And there is an associated quantity which is conserved along the equation of motion, okay? And we can immediately find out which are these conserved quantities just applying the Euler-Lagrange equation to each of the four components that we have there. So for example, if we take the first one with respect to t, we have this one, okay? So the Lagrange does not depend explicitly on t. This is a cyclic variable, okay? So we have that this object here, between parentheses, is equal to a constant that I'll call E, okay? And it's very, very easy to see that this is like well, it's like, can be associated with the energy for unit mass of the test particle, because essentially, if you see this equation here in the far field limit, so for a weak gravitating sources, essentially, and you write this for a Schwarzschild black hole, you have that this T is equal to this object here, okay? But at infinity, this term would be completely negligible, okay? And this object here, far from the source of gravity, okay, in the weak field, in the far field regime. This is just for a massive particle. This is dt in d lambda, and if I assume that the lambda is the proper time, this is just the gamma parameter, okay? So this is really the energy for unit per particle measured at infinity, okay? So I can associate this quantity with the energy for unit test mass of my particle. In the same spirit, if I consider the other cyclic variable, I find the same. And this time, let me call the constant L, okay? Which can be associated again, instead of the energy, to the angular momentum of the test particle. Now, we can simplify a bit the equation of motion by looking at theta, okay? And because the equation for theta will look in this way if you apply the Euler-Lagrange equation. Okay. And this is actually, you can look just this applying the derivatives to the Lagrangian here. Now, since we are working in a spherically symmetric space-time, I can just choose to be that theta t equal to 0 equal pi over 2, and I can also fix the velocity to 0. But this equation here will tell me that the second derivative will be 0. Okay, so if the orbit starts planar, it will remain planar. So since, again, I'm working a spherically symmetric background, I don't need to, I can just set up t equal to pi over 2. I can simplify all the sin and cos that I find in my equation there. Okay? Finally, for our purpose, the most important quantity is the equation of motion for the r variable, okay? And in particular, we can find this using the normalization property of the force velocity, okay? Where this parameter k here is equal to 1 for massive and 0 for massless particle. Okay? This is why this is useful, because if you just, so this is, of course, you can write this thing as this, okay? And where u is just this object here. So if you replace for each u the values of these with the values of t dot, phi dot, yeah? Yeah. It must be minus. Yeah, it could be this one. Yeah, it could be, yeah. Where? Well, it's, yeah, for our purposes, well, I don't know, yeah, it could be. Yeah, no, I think that the minus one, it goes if you use the other signature. But okay, I mean, it doesn't really matter for the discussion that we're doing now. So the point is that, let's keep even this as k fixed. I mean, we don't even need to, the important discriminant will be between something which is different from 0 and something will be 0. So the point is that if you replace everything here, so the expression that we already find for d phi in the lambda, dt in the lambda, and of course the d theta in the lambda will be 0, but this equation here will essentially give you this expression. And let me okay, so that r dot square, okay, is equal to what we call the energy square minus divided by f minus L square divided by R square plus k, okay? Now this is particularly important because you can rearrange this equation here, as you have seen in the first, well, year probably of physics. So for the orbital, well, the motion of in Newtonian gravity, Okay, so you can define an effective potential, okay, that takes two values depending on the particular form of the on the normalizations. It will be one of the inside here there is the constant k. Okay, and in particular there are some specific features. Okay, so let's focus now on the Schwarzschild space-time, so it's going to be a bit more easy to work with R, M, and whatever. So this will be our 1 minus 2m over R, and this will be the same, and we'll simplify. Okay, so let me call here V effective of R. So for massive particle will be E square, actually, let me rewrite let me call it this Vk of R, okay? And for the Schwarzschild space-time, let me write this equation here as in this way. Or actually in this way here, okay? Because in the Schwarzschild space-time, this factor here and this factor here just simplify, okay? So I have the energy here minus this term here, which is independent of energy. It just depends on the angular momentum, okay? And this is really, really a Newtonian picture of the story, okay? And so this V effective here is going to be given just by these two terms multiplied by h, which is 1 over minus 2m over r, okay? Now, this Vf will take two different forms. So this is for massive particle, and this is for massless particle, okay? Immediately see that for massless particle, the angular momentum just acts as a scale in front of everything. So it's an overall scale of everything, okay? And actually, we can even, since we are dealing with this, okay, if we take our affine parameter lambda, and we rescale the parameter like this, okay, it's always possible, because if you take the affine parameter and you make a linear transformation like the old one multiplied by constant, this would be again another affine parameter, okay? And in particular, by this, you can write your equation for massive particle in this way. Okay. It's very, very simple, because the only things that you need to do is rescale the affine parameter, replace, change the derivative here, okay, and there will be an overall factor of L, will just simplify, okay. But this guy here, we call it the impact parameter, where B square is this object here, okay? So this is the particular important equation for us, and for a massless particle, okay? And this one is for massive particle on top of it. Let me just cross also the potential for the massive one. Okay, this is particularly useful because, I mean, we can really apply all the things that we have done in the first course of mechanics to understand the stability of orbits, okay? And actually, stable orbits, and in particular what we are interested in are on circular orbits, okay? Circular orbits corresponds to orbits which are r dot equal to 0, okay? And in order to find this, I think I can cancel this blackboard here. Position is just given by, well, v dot effective of r equal to 0, okay? And if you take the effective potential, okay, and, well, actually, let's take this one without specifying k, so it will be more general, okay? And you just take derivative of this object here. It's very, very easy, also because E and L are constant. You will find this equation. These are all very simple algebraic manipulations, so I just want to give you the result because it really doesn't matter. Okay, and this is solved for just this. Okay. Now, what does this equation here tells you? That for k different from 0, the orbits, since this is positive, I mean m is positive, okay, and for k equal to 1, we can have, so for massive particle, we can have orbits only for circular orbits only for r larger than 3m, okay? For massless orbits, okay, which this is equal to 0, you have this equation identically equal to 0. This set up the location of the only circular orbits for massless particle to be r equal to 3m. Okay, so for massless particle, there is only one solution to this problem. So you have circular orbits only when this guy is equal to 0. Okay, k equal to 0, this is equal to 0, and you find out that this is in r equal to 3m. Okay, so we found out two things, that for massive particles there are circular orbits for r larger than 3m. For massless particle there is only one opportunity, and there is r equal to 3m. This is a number that you have really to print because it's extremely important for everything, this 3m. Okay, for quasi-normal modes, for stability. Okay? But to better understand the stability, you can also compute the second derivative of the effective potential. And if you make, again, derivative of this object, or the first derivative of this one, you will find something like this. Okay? And the important factor are r minus 6m and r minus 3m here. So we found that for r larger than 6m, this is positive, okay? So this is a stable point, these are stable points for the orbits, okay? So stable orbits for massive particle exist only for r larger than 6m. And in particular, the limited case, which is r equal to 6m, is called the ISCO, so the innermost stable circular orbit, okay? And this is the last one of these orbits. Okay. For r smaller than 3m, well, we don't have any stable orbit, okay? So for r, we have only unstable orbits. Another useful things, because we can use our intuition from classical mechanics, is to draw the effective, to make the kind of energy potential so let's assume that for massive particle, okay, let's assume that we take the energy of our particle equal to 1. Okay, this is just a simplified assumption, and I draw the potential that is behind the blackboard, behind the panel there. So the thing is that So the height of the potential in this case will just, if we fix the energy, will just be given by the values of L, okay, L over M, okay? And in particular, there are some critical cases in this particular configuration. Yeah, it was this one. There are, there are some particular cases, okay, depending on the value of M, for which you have turning points, okay? So points for which R dot is equal to 0, and this means that if I take a particle which is falling to the black holes, this particle, will be reflected back, okay? Now, the form of this, the potential and the turning point will be determined by the values of L over M, okay? And in particular, for L, in this particular combination, larger than for M, you have real turning points. There's always a solution which gives you R dot equal to 0. So you have turning point. This means that all the particles coming from this, at some point they can be reflected back. Okay. Otherwise, you won't have like a turning point. And there is critical value for which is this form of the potential here, which is for L divided by M equal to 4. Okay? For a smaller value also, you have like that the maximum and the minimum just merge, and you will have that the potential is given by this branch here. Okay? But the important point is there is a critical value of the angular momentum for which there is turning point. Okay, so a value for which the velocity R dot, the radial velocity, is equal to 0. Most interesting for us, more interesting, is actually the form of the effective potential for M equal to 0, so for a massive particle. Okay, and this is given by this. So there, at the blackboard, we have written this formula here. When there is this guy here is the effective potential there. So depending on the values of the impact parameter, you can have a turning point here, okay? And so the orbits of your massless particle will change. So the potential here has a maximum, which corresponds to 27 m squared, okay? And whatever this relation is satisfied, whatever one of the impact parameter is smaller than 27 m squared, you have turning points. Okay, so the massless particle can be reflected back. Okay, the critical value is that when b squared is equal to 27, the maximum here. Okay, and this value here actually correspond to b equal to 3 square root of 3m. And the maximum of the potential is just at 3m. Okay? So you see from the potential, the discussion that we were making just from algebraic manipulation there, okay? You only have one maximum, okay? There is one possibility to have just one circular orbit, but the orbit actually is not, as you can see from just by intuition from the form of the potential, the orbit is not stable. Okay, it's an unstable orbit. So for massless particle, not only you have just one possibility, okay, the light ring, this r equal to 2m is called the light ring, but the orbit is also unstable. This means that if you kick the particle, it will go in or run out of the black hole. Okay. what we can say more about this. Okay. So we can just summarize this discussion. For massive particles, we have stable orbit only for area larger than 6m, okay, and 6m is the ISCO, okay. For m equal to 0, we have only one orbit, which is as r equal to 3m, and it is unstable. Here it is, okay. This is r equal to 3m, okay, this is unstable. And the critical impact parameter, we have seen before, so when 1 over b square is equal to 1 over 27m square for massless particle, so for m equal to 0, critical impact parameter for the capture of the particle means that the r dot will be 0, okay? So the wave of the mass or the massless particle will be captured by the potential here is for b equal to this value here. And actually this parameter here corresponds to 3m. So we don't only, for massless particle or waves, we don't only find that r equal to 3m is the unstable orbit, okay? But it also corresponds to the critical values for which we have captures of wave or massless particle. This is particularly important because there is a strong connection between the excitation of quasi-normal modes and the light ring, so this 3m. So essentially waves are just trapped at the light ring, okay? They excite the mode of the photosphere and then they are relaxed away. And there is this connection between these waves, which are relaxed away from the photosphere, and the quasi-normal modes that we use to describe the post-merger signal of black holes. There is another important feature that I want to show you, is that it's a very, very, simple result. I think that all of you have already done this in, in all the possible textbook. But, so, if you take the radial equation, well, just this one, and actually, no, let me write this correctly. So if we switch the radial equation in terms is for a massive particle, instead of the FM parameter, we use the coordinate time, we'll actually find this relation. So that the coordinate time here, there is probably a dr here, measured by an observer at infinity, is as equal to the energy. This is the f that is in front of the metric, okay, plus something, multiplied by something, okay. There is an important feature here, okay, that if you take the limit r equal to tm, these things here will explode. Okay, so the coordinate time measured at infinity by an observer will be infinity. This means that whatever you put at the horizon, the signal that you will get is just frozen there. This is an important consequence because, it essentially gives you that it's really, really impossible to test the horizon. Because whatever you put to the horizon, it will never have the time to be seen from a distant observer. It will never have the time to go there and come back to you, because it will take an infinite amount of time. And this is also important because you have, when people talk about quasi-normal modes, the connection with the quasi-normal modes is not at the horizon. Because whatever you get, I mean, you cannot have any signal from the horizon. But as we will see, the connection to the quasi-normal modes will come from this guy here, which is the point, which is the last orbit where waves or massless particle can be captured. The horizon, for which you cannot see anything, will only play a role imposing boundary conditions to your differential problem. But you cannot see anything escaping from that. This is my timer, right? So I think that I cannot explain anything else from this. So this afternoon, you will work about how to extend this formalism here to slowly rotating objects. And when I mean slowly, when I mean slowly rotating, I mean that so the exercise will be how to so I don't want to talk about care, because although it's extremely beautiful, this is a pretty unique scenario. Okay? And it's not very useful, at least for exotic compact objects, because in most of, well, actually, all of the objects that we know, you don't have exact solution for rotating objects. Okay? So the things that you do is actually working to extend your line, the line element in this way. So you take a spherically symmetric background and you perturb this background, okay, in order to consider the effect of small rotation. Okay? And this guy here is a guy that will depend on rotation here. And you can include, well, as many as you have time to compute terms in the rotation here. This is a powerful tool which is well, based on the Arthurton approximation, okay, of perturbing a spherically symmetric object. And it's particularly useful to build also slowly rotating solution for not only neutron star, but also for exotic compact objects. So this afternoon, you will have to deal with building a very, very simple solution at the second order index field from this guy, and try to see some features of the geodesic motion for a slowly rotating object. So, for example, how these guys change if you add the effect of the spin, the ergosphere, and any other problem related to the effective potential. Okay? And I'll be here, I mean, of course, all day, so if you need something else or you want to talk or whatever, we can talk all day.